I've always thought brain-computer interfaces are incredibly interesting, but the idea of them being invasive, like plugging something into your brain, just seems like really, really disgusting and really, really wrong. And I don't think we have to do that at all. It's a bit like plugging something into your heart to measure, the heart, right? And the pulses and apparently the heart actually gives off like the strongest electromagnetic signals of the body, interestingly enough. I thought maybe, I wonder if it's possible to make like a brain-computer interface, but like targeting the heart, so I don't know. Anyway, this is kind of how these things seem to work. So if you look into EEG machines, I think it's like electroencephalogram machines. Essentially what you have are a bunch of silver electrodes, and an electrode is like two pieces of metal, right? A positive and negative piece of metal. And you're measuring the signal between these things. So, and the signal is, it's like an AC signal. It has a certain amount of voltage. It's really, really small because the skull kind of acts as like a filter, and you can't really get very strong signals, which is why they, wanted to plug things into people's brains, right? Like Neuralink, because you get a much clearer signal from it. But I still think it's clear enough that we could work off it, right? And these things have been in the works for, years and years and years, right? And now it's to the point where you can actually buy one of these things for a couple $100, like a headband or a whole headset and the processing unit and all that. Used to be, thousands of dollars. It's actually not that complicated of hardware, because really all it is, as I said, it's an electrode, which is these two pieces of metal, and then you wire them back to essentially what you have to make is an amplifier with filters. Now, usually amplifiers have capacitors and resistors all around the transistor. If you understand electronics, transistors are the basis of amplification. A transistor is essentially you plug a signal into the transistor and it opens and closes depending on the signal, right? And then you run some electricity through the transistor and you amplify the signal that way, and you probably create extra noise, and you probably need a preamp, maybe, I don't know, because again, these signals are super weak. You might need a preamp, which just amplifies the signal into a, I guess, I don't know, do you call it like a post amp or something, an after amp, whatever. And you also need filters, and if you've played around with music, all this stuff is exactly the same as a synthesizer. It synthesizes a great way to learn about signals and filters and amplifiers and all these things. You'll heard like cutoff filters and high pass, low pass. If you played around like FL Studios and you got all this stuff. Now you need to capture, because the low signals, 0 hertz is DC energy, and we want to get rid of that. And the way you do that is you have a I believe it's called forgive me if I get this wrong, a coupling capacitor. Essentially a capacitor, if you put a capacitor in your after your signal, it takes away the DC. That's what capacitors do, because only AC can go through them, because it's like technically you can't fit electricity through the capacitor because it's two pieces of like foil which charge a positive and negative electrostatic or dielectric field essentially. And then you got the separator, so only AC can go forward because it pushes forwards and backwards, so to speak. So going on, you use that, and you're going to have to use another one to filter out high frequency. And basically these filters use, if you look into high pass, low pass, they use a resistor and a capacitor. or they use a resistor and an inductor. And the difference between the two of them is if the resistor is in series and the capacitor is in parallel, I believe, or the capacitor is in series and resistor is in parallel with the signal, and essentially one of them will kind of drown out the AC, which is the bypass. The bypass lets DC through, and it like pretty much baits the AC into getting drowned out, so to speak. So anyway, that's kind of what they actually use on the electronic side for these brain-computer interfaces, is amplification of the signal and filtering, because you want to get rid of the DC and you want to get rid of, apparently you want to get rid of anything above about 50 hertz or 60 hertz, give or take, even though if you know brainwaves, 50 is like low gamma. Your gamma goes up to 100, even 200. They've measured up to what, like 500 hertz even with all of this stuff. So you know it goes pretty far. But apparently you don't like those signals aren't as easy to. You need like really fine equipment, so to speak. It's like with gigahertz oscillators and probes and such. You need really like expensive equipment, so it's easier just to work with like 0.5 hertz to 50 hertz, right? So next, your hardware is probably not going to be perfect. You can buy these, it's called like is it AD something or PM, I forget, there's this like circuit board with some integrated circuits and some other stuff which basically does the filtering and amplification. If you look up EEG circuit boards and like Arduino modules and all that, you'll find them. I believe they only work for a single electrode. Now you have to think like more electrodes will add more resolution, right, to the signal of what you're getting from your brain. But at a certain point, I think about 512 electrodes is like kind of the max you really care about. I'm pretty sure in Neuralink they start off with about 1,000 KB, so to speak, of kilobyte of like filter, or kilobit, I guess, of electrodes, so to speak. And that's the thing where they plug all those electrodes into the brain. They essentially act as the same thing as the non-invasive, as the silver pieces of metal. Now, I hypothesize that if you had, because there's this issue with like people, you want to use gels to like get a good electrical connection to the head. I imagine something like a push pin kind of. What would it be? You know how like a vinyl record player, it like bounces up and down on the waves, but it still hits the grooves? You get what I mean? Imagine if you had some kind of electrode that like pushes out like a very weak piece of metal, like 2 pieces of metal or whatever. And so it, like, even if you have hair, it still pushes those into the head, and you would round this off and add plastic and rubber and all that stuff to make it so it doesn't like stab you, because you want it to be thick, so it's nice and thick, but it pushes in, so everything's pushing in to get a nice connection. Otherwise, hypothetically, you could use like magnetic electrodes or something. We'll get into that in a minute. Right, so then we have our filtered and amplified signal, and we hook this into the software layer, and the software layer is greatly enhanced by machine learning. And as I said, you have to pick your array size. I'd pick about 32 electrodes for like maybe a professional thing. If you're just testing things out, you can probably just have about like 4 standard electrodes, or even like 2, or even just 1, just to test things out, right? But as I said, more electrodes means more wires, and it means more points of error, and then it means more amplification. I'm sure there's like people who are really good with electronics and figure out better ways to have individual signals and channels for all this kind of stuff, but eventually you're going to have way too many channels, and it's going to be a pain in the butt to do too many. So that's why adding more is actually not, is counterintuitive. It's counterintuitive. It's like adding more eventually gives kind of diminishing returns and complexity issues. So that's kind of not the really thing that solves the issue. Now, going on, it seems almost software is actually what's solving a lot of issues. If you looked into Neuralink, actually, they use a lot of, I believe, machine learning and AI and all that. And actually, as the software progressed, even though a lot of their electrodes in the brain were being dissolved and disintegrated and destroyed and all that, they actually got better and better and better readings. And the guys who are doing it can control the computer way better because of the increasingly better software, which makes me think that we can make this, right? Because this is, at least for controlling, basic computer hardware and such, I think this will work. So essentially you will, so this is you get an AC thing and you convert it to a digital signal. So you're converting each electrode to like 0 to, I don't know, 50,000 or something digits, and it can go between those. So it'll give you like a number, like it'll give you like 2,000 if it's on the low end, or 1,000, or it'll give you 40,000 if it's like really on the high end. So you'd think about something and you'd be like, okay, if I want to think that this is yes, then I'm going to check what the electrode data, digital data is, and you write a program essentially through using machine learning so that it tracks every time you click the button and you go yes, it says, okay, this is this is like the digital signal, technically the frequency, AC frequency and all that is of yes, right? And you just keep doing that, and you keep, reinforcing it in. But also through the software level, what I forgot to say is you need to add more filtering. You need to filter out the signals again, and the reason you do it hardware-wise is because you'd create too much electromagnetic disturbance within your hardware. You'd create too much like disturbance, and then when it gets to the PC, it's just all muddled and messy and all that. So you need to refilter again, right? As I said, through machine learning and through software, you just keep honing it in, because it's a bit like how AI works, where AI has like these matrices, and if you understand, a matrix is an array. So it's like, imagine like a two-dimensional video game or a chessboard. A chessboard is a matrix. It's like, squares. It's like a row of squares and a column of squares to make a board. And then imagine like one area on the chessboard where you put a pawn means like yes. That's like how the computer understands everything when it comes to like machine learning, right? So the letter A is this complex 0 and 1 matrix, I believe, which is how you would make these matrices. You would make these like data patterns, you can think, for everything. So for up, down, left, right, left click, right click, A, B, C, D, whatever you want to control. People controlling drones, people, musical instruments, just whatever you want. And as I said, you have to record these. Similar when you're playing a video game and you record like A, B, C, D for the controller, for like, to know which one. Just say if you're using like a controller that's, I don't know, not the correct controller or whatever, and you've got to reset the buttons, right? You know what I mean by that. And then eventually you have this, you're running this software in the background which understands you and understands, so what you would do also, you would have a mode where you just sit there and you kind of meditate, or you do nothing, because you need the software to understand your base frequencies, so to speak, the base data, so that it doesn't do anything. And you would also want to be meditating daily, because you wouldn't be able to control this very easily if you don't meditate. Maybe, I don't know, maybe you'd have to practice more with it, I guess. So that's kind of how this whole thing works. Now, going on, limitations, as I said, there's a limitation kind of physically with array sizes and electrodes and all this kind of stuff, and how many amplifiers. That could be partially fixed through electronics. There is limitations on, obviously, like processing power. You wouldn't want this thing to be too bandwidth hefty. Ideally, you would want this to be able to run on a microcontroller, so hundreds of megahertz max, gigahertz, like a gig or two. Like, I'll be able to run it on like an old laptop at least, right? So you want this to be more efficient. So you could use it for anything. Then, of course, limits is, different people have different capabilities with their brains. Limitations on different areas could cause signal disturbances. These electrodes will pick up the power lines in your house, the temperature differences, all this kind of stuff, which you partially software filter out as well. So that's how you fix that. Next is, so this thing works for basic signals, and it works for simple stuff. How would we create a soul translator, so to speak? And I had the idea of that, imagine the brain's current magnetic field. That's kind of like the soul, or it's one way we could look into the soul, so to speak. So it would be the brain at its current state at this second, right? Constantly changing, which is the magnetic fields of the brain. There's this thing called MEG, magnetic, I guess, encephalograph, or encephalographology, or whatever it's called, right? So MEG, you can look that up. Problem with that is apparently the machines are like millions of dollars and they need to be cooled, and this goes into like quantum computing and all kinds of stuff. But essentially that is the next level of this, and that's like a soul translator, so to speak. Now I think you could make a pseudo soul translator, or a pseudo brain translator, by using arrays of electrodes at certain parts of the brain and targeting specific areas. So you target the back with electrodes to target like the visual stuff. Is it the front that's the motor cortex? The front's like the willpower or whatever. So you'd put like different sensors, specialized sensors at different areas of the brain, still EEG, still electronic sensors, to create I believe this is what they've done. They've created like a pseudo magnetic field, or it's almost like an emulator, essentially. They're emulating what the magnetic field of the brain would be like. And then, of course, there's the idea of using ultrasounds to bounce stuff off areas of the brain. That's how they've done the smell, the virtual smell, creating virtual smell. They've done it through ultrasound. If you look into that, someone posted that on Twitter. It's pretty interesting. But otherwise, I don't have the money for any of that stuff, so and that's I guess for the future. But I do see that as a possibility, because eventually with like full dive VR, you will want a current snapshot of the entire brain to fully immerse yourself in a virtual environment. So again, the way I see it is these EEGs is more of like a low-level signal thing, the same way a keyboard is, a keyboard works and it gets you around, and it you can do everything with it. But then eventually the mouse came. Right, the mouse is a little more feeling, it's a little more advanced in certain ways. That's kind of like the magnetic side of it, so you could do both with both things. Anyway, and otherwise, Neuralink has shown us that the software they have all the software already. They've been able to do this from just a small region of the brain. Who knows what happens when we start integrating more regions, the whole brain, all this kind of stuff. But as I said, unless you're like paraplegic, you literally can't move anything, I don't think you really want to put a bunch of wires in your brain and cut out part of your head, and it's just a little bit gruesome. So that's why I think the non-invasive works, and I see the non-invasive stuff, it hasn't really caught on because no one's really gone out of their way to like make this into like a video game product. Is the best way to put it, right? Like touchscreens got really popular because they went into like phones and Nintendo DS's and all this kind of stuff. Now touchscreens are everywhere. This is a thing. Before they were popular, there was like some small examples of touchscreens, and they weren't really much of a thing, and they were kind of not really as advanced, and there wasn't much software and such for them. I think it's the exact same thing where EEGs are they've mostly been used for like small scale scientific studies, but if this stuff gets released for the entertainment industry or the personal computing industry, because I do believe, the ultimate controller is ultimately a brain. Using your brain to control stuff. This is using your hands to control something is kind of primitive, right? It's less advanced. I'm interested in the idea of like virtual reality and brain control combined. So then we can like really access, the virtual world within ourselves, because I'll be honest, a VR headset is pretty good. It's not full dive VR, but the fact that it fools your depth perception, it literally looks like you are there. It literally feels like you are there because you can tell, you can tell the distance in objects. I love that so much, because it adds a sense of feeling, or a ghostly sense of feeling. Not you can't feel it with your hands, but you can feel it kind of with your eyes, So I think that's pretty good, right? I hope they advance and all that stuff. But still, if you combine that with like a brain-computer interface, it would be insane. Imagine like just playing like an RPG game like that. Envisioning you have these hands which you can feel, because it'd trick your brain even more into thinking that it's real, because of the depth perception. It's just like how much fun that would be. So I don't know, I just envision that for the future. So anyway, that's mostly what it is. As I said, you basically electrodes feeding the signal into filters and amplifiers. It's basically like musical synthesizer stuff, feeding it into a computer that filters it more and then digitizes the signal, and then it's just using a software layer with usually lots of learning. You wouldn't have to use machine learning if you don't want to, but it would help things out, right? To then understand what signals relate to what feeling, what thoughts relate to what things, and so you can pick hotkeys, and you can pick what up, down, left, right, A, B, escape menu, shift or jump, what run, what all this kind of stuff. We'll just leave it at that. I think that's good. So of course, look into low pass, high pass filters and amplifiers if you want to know about the electrical engineering sides and electrodes and all that stuff, and then look into the software side of it. It's not as complicated as you might think, I guess. I'm sure when you get down to doing it, it's a bit of a pain in the butt, but otherwise. Anyway, I hope you enjoyed, and do have a good day or night.